Hi, Aaron. Can you start?
Yep. Okay, so this paper is called Boosting Fuzzer Efficiency, and they are doing so using an information-theoretic perspective. So just an overview on fuzzing. So it's also known as fuzz testing, which is just one automated software testing technique. And it provides, and how it does it is just by providing like random data as inputs and trying to get some outputs from the program. And hopefully they can get some inputs where the program gives some unexpected behavior so that you can identify bugs from this. So it's actually one of the most successful vulnerability discovery technique. So this paper takes an information-theoretic perspective to fuzz testing and tries to understand fuzzing as a learning process. So um, they determine a fuzzer's efficiency by determining the average information each input reveals about the program's behaviors. So basically, like, because each input that they give to the program is different, so they want to know which input provides more information about the behavior of the program. So, for example, if the fuzzer exercises mostly the same few program behaviors, then we can say that this fuzzer's entropy is small, or the seed for this fuzzer, the entropy is small, and hence this seed is not efficient at discovering new behaviors. So they propose this new fuzz testing called Entropic, and it's basically just modifying the power schedule for gray box fuzzing, which we'll go through later. So what it just does is it assigns more energy to seeds that reveals more information about the program behaviors. And because the energy of a seed, it determines the probability that that seed is chosen for mutation. So if you,
This idea is good. Okay.
yeah,
Please
so
keep going.
you, so if a seed has more energy, it helps to maximize the efficiency of the fuzzer.
Hi, Aaron. Sorry. So would you please wait me for 5 minutes? I need to leave for 5 more minutes.
Okay.
One moment. Okay. Thank you.
Yeah. So yeah, this is just an overview of the approach that this paper does, Entropic, and we'll just be going through like the technical details. So the first thing that they introduce is that they model software testing as a discovery of species. So P is the program to fuzz, and D is the input space of the program. So they look at fuzzing of a program as a stochastic process, where basically you're just sampling n number of inputs with replacement. So you can actually subdivide the search space D into S number of individual subdomains, and each subdomain is called a species. So a species is usually defined based on some properties of the input's execution. So in this case, each species is defined by like, for example, a branch, because they're using branch coverage. So each branch exercised by an input xn is identified as a species. So if an input xn discovers a species di, then this is only the case if di is sampled for the first time.
Sorry. So X is identified for the species. Okay. So I got it. So the D is actually the branch here.
Yeah, so this is the di is like a branch. So they call this the global species discovery. So they define PI as the probability that the nth generated input xn, it belongs to species di. And from this, they get the global species distribution. And from this distribution, they just get the expected number of discovered species using this formula.
Can you explain a bit?
Yeah, so this formula, they didn't explain how to get this. I think this is like the like the standard formula to get the expected number based on
Here n is the parameter. If n is parameter, so here p is the probability that an instant related input xn belongs to the di. So okay, the pi is corresponding to di, right? So whatever how large it is, how large n it is, will the probability pi change?
sorry, can you say it again?
I'm asking that, for example, suppose n is 1, and when n is there make a difference when n is equals to 1, 2, or 3, 5 for the value of p?
For the value of
Yeah, well, the value of p, actually pi corresponding to a species di, right?
Yeah.
And when I'm asking when n change, will the value of pi change?
It should be different because it's for a different input.
Yeah, so the n is more more to describe the frequency of a species di, right? And the expected number of discarded species si. So can you mention a bit about the physical meanings or the semantic meanings of sn?
Yeah. So for example, given a program, like the SN should correspond to how many species there are. So in this case, it's just corresponding to how many branches there are. So yeah, actually there's a graph. Yeah, so this is just an illustration. So you can see that the maximum number of species for a given program is just S. And you can see that when you increase the number of test inputs, it should increase the number of species that you discover. And so they define this discovery rate, the change of n. So basically, how many species you discover given test input number n.
I got this one, but it seems that the SN, there's a formula for SN, right? So that means suppose I sampled 1,000 test input, and we somehow have an expected number, an expected number of discovered species. And can I look into the formula again? So I somehow not sure why that is the formula and how this formula, and each PI is different, right?
I think I can help to explain this. So PI is the probability that for example, for a specific PI is the probability to find one species. So 1 minus PI is the probability that you don't find this species, and you sample it for n times. So 1 minus PI to the power of
So that is
that is the probability that when you sample n times, you don't find this species. So 1 minus this probability is the probability that when you sampled n time, you will find this. You can find this species, and then you sum up all the species.
Yes, I got it.
Yeah.
So, yeah, that's an excellent explanation.
Thank you.
Yeah. So, but the point is that the PI seems to be a constant, right? So that a sample one So is that true that the PI is a constant probability, or sometimes when I sample an X, of course, if we just talk about uh, in a forest, an unknown forest, when I find a species A, maybe it is independent from another species B. But for software testings or fuzzings, when I find it, when we cover a branch A, it might improve the probability to find a branch B, right?
Mhm.
Mm.
Yeah.
Okay, maybe that is just please.
Yeah, I think this is a constant, like the PI. So you shouldn't change.
Mm. Yeah, maybe that is estimation, but it is actually a good estimation with the assumption of all the species are independent with each other.
Okay.
Okay. Thanks, Xianglin.
Yeah. So they define the discovery rate as such, and the idea is they can abort fuzzing when insufficient progress is made for a long period of time. So if the discovery rate is less than theta for some theta, they can stop the fuzzing process. So to define another thing, which is the local species discovery, because basically when you generate uh, a like a test for the program, you divide them into many different seeds. So this local species discovery is for each test seed. So all species that can be, so define the T's neighborhood as all the species that can be found by fuzzing a seed T. And then probability of Ti is the probability that the nth generated input is generated by mutating the seed T that belongs to the species Di. So this formula is basically the same, just that now instead for the whole program is just for one seed T. So by law of total expectation, the global and local distributions are related, where QT is the probability that the fuzzer chooses seed T. So C over here is just they call it the corpus of seeds, which is basically just the whole pool of seeds. So now if you just substitute this PI with this formula with the previous expectation Sn, then you will get this formula.
Okay.
Yep. So just talk a bit about information theory. So the entropy that they use is called Xianlin's entropy, which is a classic measure of information. And it measures the average amount of info in each sample, in each input, which about the species that can be observed by executing the program P. So when there are S distinct species, then use this formula for the entropy H. Yep. So just a illustration
About the information theory, the entropy.
Yeah. So like each urn or each box over here is like a test seed or the input, and the colored balls are like the different species. And basically, you can see that if there are a high number of equal probability outputs, then there'll be a high entropy. So for example, urn 3 has 3 different outputs, so it has the highest entropy among the 3 urns. However, Shannon's entropy is defined for distributions where each input belongs to exactly one species. However, this is not the case because an input can belong to multiple species. For example, one input can execute multiple branches. So what they do is they just normalize the probabilities. So H instead of PI is P prime I, where P prime I is just normalizing the PI out of the sum of all the probabilities.
So here it is the sum of pi, the pj's. That means to sum up all the pj's. Let me think about it. So why this works, and why this normalization can work?
So this one they didn't really explain, but the idea of this normalizing came from another paper which they referenced. Yeah.
So let's assuming so how, let me digest a little bit. So assuming that there's CFGs, and this is maybe A is smaller than 0 and B is bigger than 0, right? So very simple. So here it's minus 1, 1, sorry, minus 1, minus 1, and here is minus 1, 1, right? And this branch has been executed twice. So in this case, and also we will have another sample. It means 1, 2. It's possible, right? So this is I1, this is I2, and this is I3, right? And this branch, let's talk about 1, 2, 3, 4, right? So in this case, P1 is 1 over 3, P2 is 1 over 2 over 3, and the P3 is 1 over 3, and the P4 is 1 over 3. Am I right?
Yeah.
So if we sum up all the probabilities, so the problem is that if we sum up all the probabilities, these probabilities, I see. So the point is that if we sum up all the probabilities, the probability, if one input can belong to multiple species, that means the overall probabilities will be over 1. So this idea is that we're going to just do a very simple normalization here. Okay, please go on. So we have okay, so we just need to expand the formula like this. We will have we can calculate an entropy like this.
Yeah, so they just substituted P prime with this formula, and they get, when you expand it, you get this formula below.
Isn't that this formula is 1, and this item will be 0? Am I correct? Or there is another? Because you can look at these probabilities. If we sum up all the PJs, the PJ has to be 1. The sum has to be 1. Hello?
As in, it can be more than 1.
Oh, sorry. My bad. So the sum of PI prime is supposed to be 1. Okay. It's over 1. Okay. Thanks, Aaron.
Yep. So sorry, another so now, because there is the local species distribution for a seed T, so basically you just substitute the P, the probability P with the probability P of seed T to get the local entropy H T. So this HT entropy, it just quantifies the information that fuzzing a seed T reveals about the species in T's neighborhood. So if HT is bigger, then it means that fuzzing seed T has gives higher information. So another thing they did is they have to characterize the general discovery rate using the entropy, and C over here is just a normalizing constant. So, and basically this discovery, this entropy measures the species discovery rate over an infinitely long running fuzzing campaign. So the reason they use this formula is because if they just rely on the total number of species discovered, which is S, this provides no insight on the efficiency of the discovery process. So you can see that the diminishing factor of dividing by n over here, it reduces the contribution of species discovery as the testing effort n increases. So they had to use this maximum likelihood estimator for the entropy. So they estimate the entropy based on how often they have seen each observed species. So they one thing they introduced is this incidence frequency y. So for a species di, the incidence frequency y is the number of generated test inputs that belong to this species. And using this incidence frequency, they can get the unbiased estimator for pi, which is just the frequency divided by the total number of generated test inputs. So they can attribute. So now they can estimate the entropy H using the MLE. Yeah. So they just substituted the pi for this unbiased estimator. So so this is what Entropic does again. So it's just an entropy-based boosting strategy for gray box fuzzing. And it tries to maximize info that each generated input reveals about the species in a program. And Entropic is implemented into the popular gray box fuzzer lead fuzzer. So it starts with a population of C inputs, and so this is what lead fuzzer does originally. It just starts with a corpus of C inputs and continuously fuzz these inputs by applying random mutations. And whenever a generated input increase coverage, it is added into the seed corpus. And the probability of a seed chosen for fuzzing is called the seed's energy. And the procedure that assigns the energy to each seed is called the power schedule. So originally, lead fuzzer assigns more energy to seeds that are found later in the fuzzing campaign, but Entropic just modifies this power schedule. So this is just a high-level overview of the Entropic algorithm. So the boxes in green are the one that is modified or added by Entropic. So initially, we'll just go through this roughly. So line 1, you're just looping through, looping until a timeout, and then for for line 2, for all the seeds, they assign an energy to each seed, and this line is just called the power schedule. So for line 3 and 4, it just normalizes the energy for each seed, and line 5, it just picks one of the seed from the seed corpus with the probability of the energy. And line 6, it will mutate that chosen seed for fuzzing. So line 7, it inputs that mutated seed into the program, and then if the program crashes, it straight away returns that seed, because this is what a fuzzer does. It just wants to identify seed inputs that causes the program to crash. And line 8, if the seed doesn't crash the program and increases the coverage, then it's added to the seed population.
So I have a question here. I think the idea is quite is fairly straightforward.
Mm.
One concern is that given a seed S and we mutate the seed S and we will have its neighbor S prime. Of course, for S will have its energy, right? So given that the energy is actually calculated by the entropy, right?
Mm.
And how can we adopt the same method to calculate the energy of S prime? Oh, so if we derive an S prime, suppose S prime that does not discover anything, it's supposed to have a low energy, and suppose it actually discover a species, or covering one more branch that is supposed to have a higher energy for S prime.
Mm.
Okay, please go on.
Yep. So line 9 to 11 is a loop that is added by Entropic. So basically what it does is just for all the species that are covered by this mutated seed, it calculates the local incidence frequency. So so we go through the power schedule that Entropic modifies, and basically same thing. It just assigns more energy to seeds that provide more info about the program's species, and the amount of info about the species in the neighborhood of a seed T is measured using the seed's local entropy HT, which we saw the formula earlier. But one challenge that they faced was that they noticed that the entropy estimates for different seeds were actually very similar to one another. So there were not much differences. And this was due to a small number of very abundant species, which have a huge impact on the entropy estimate. So actually they try to find they just want to account for rare species that are found. So they define a global abundance threshold theta that only maintain the local incidence frequencies for globally rare species. So only if incidence frequency is less than theta, then it will account for this. Then it will keep track of this local incidence frequency. So these are the research questions that they have. You see what is the empirical coverage improvement over the baseline? How much faster are bugs detected? How does the abundance threshold theta influence the performance? And also what is the cost of maintaining the incidence frequencies in the fuzzer? So this is the experiment setup. They implement this Entropic using lip fuzzer, and they compared Entropic with lip fuzzer on two benchmarks that contains 263 programs that are applied in many different domains. And they conducted 1001 hour and 2006 hour fuzzing campaigns. So for the first question, what is the empirical coverage improvement over the baseline? So from the results you'll see later, mostly there's an increase in coverage with statistical significance, and entropy is also about twice as fast as deep fuzzer in most cases. So this some results. So the dotted line is the graph for entropic, and the solid line is for lip fuzzer. You can see that the so the number of features is basically the number of species that are discovered by the fuzzer. So you can see that for most of the graphs, the entropic line is higher than the lip fuzzer line. So it means that for given a certain time, Entropy can discover more species than lead fuzzer. And the vertical dashed line just shows the timing that the Entropic achieves the same coverage that lead fuzzer does in the whole of 1 hour. So, for example, in this library PNG graph, so lead fuzzer in 1 hour it discovers 300 species, but Entropic discovers that in about less than 15 minutes. And the values on the bottom right of each graph, it just shows the Varga-Delaney effect size. So this effect size is just a scale from 0 to 1, and if it is more than, and if this size is more than 0.5, it means that Entropic performs better.
Okay, please go on.
So we can, yeah. So for this graph, we see the x-axis is the percentage of subjects, and the y-axis is how much more coverage does Entropic achieve. So, for example,
So why here is the so why is it supposed to be negative? So 200% and minus 100%.
yeah. So, for example, like
Oh yeah, I guessing there's a comparison.
yeah, so for example, like 20% of the subjects, Entropic can achieve 10% more coverage, and this is after 6 hours of running the fuzzer, as compared to the previous graph, which is just 1 hour. So you can see here that about 23%, the dotted line shows the inverse graph. So basically about 23% of the subjects, Entropic actually achieves less coverage than lead fuzzer. So from here we see that the coverage difference was mostly marginal, so less than 2%. And for all these subjects, the subjects were actually much larger. So they had actually like twice the number of average branches. And this caused like the performance overhead, which is incurred when they try to
The subject. Okay, so there's the subject means a program.
yeah.
Okay, so in different programs they will have different performance. In this diagram, and it means that 23% of programs actually where on the entropic actually perform worse. And the coverage difference was marginal. And how do the okay? So the point is that so most of them is marginal is here, right? So this means the coverage difference, the marginal difference, it only appears in this area. Am I right? Oh, sorry, it's not here. So yeah, I'm correct. So among the 20%, there's maybe half and more than half. They only have a worse coverage less than 1%, right?
Yeah.
And but the interesting is that in some cases, the Entropic is actually much worse than the old approach.
Yeah. So they didn't really account for this one.
Okay.
Yeah. But yeah, for most of the subjects, they were very large, which incurred the performance overhead of keeping track of the incidence frequencies. So this is another graph to show the time to coverage, and basically for X% of subjects, Entropic achieves the same coverage in Y number of hours. So for example, for 50% of the subjects, Entropic can cover the same coverage in 3 hours as compared to lead fuzzer that covers in 6 hours.
let me have a check how to read this diagram. Would you please repeat it again? So
So-
they have 264 subjects, and how to read these lines.
So,
For example, here, suppose 50% of the subjects. So how can we read these 3 hours, and what do these 3 hours mean?
so it means in 3 hours, Entropic can achieve the same amount of coverage as deep fuzzer, where deep
Oh,
fuzzer,
6 hours. I got it. And here means that the entropy needs additional time, right? Need additional time.
is
So
the inverse.
yeah, the point is that actually it should reverse, somehow to reverse, but it does not have a space. So it's just reversing back here. I get the point. Thanks, Aaron. Please going on.
So Entropic achieves the same coverage almost twice as fast for about half of the subjects. So this is another graph to show that Entropic gets better at achieving coverage after some time. So in this graph, it shows that for X number of minutes, Entropic achieves more coverage for Y% of the subjects. So for example, you can see here that after 10 minutes, Entropic achieves more coverage for half of the subjects, and deep fuzzer also achieves better coverage for half of the subjects. So basically, when you go after the 10 minutes mark,
the proportion of wins. Let me see. So after 10 minutes, so after 10 minutes, and how to compare on Entropic and deep fuzzer, achieve more coverage for Y number of subjects. So here the point is that from very start, actually from the very beginning, the deep fuzzer and the Entropic are the same, and after 10 minutes, so the Entropic actually covers 5%, 50%, have a better performance on 50% of the subjects. And after 6 hours, it is actually better than 80% of the subjects. Then live further. This graph is kind of interesting. Maybe we can adopt the idea like this. Okay, please go on.
So they both break even at about 10 minutes, where thereafter Entropic wins all the way. And they hypothesized that Entropic is more effective as saturation is being approached after a long campaign. So because later on in the campaign, it might be more important to choose high entropic seeds. So how much faster are bugs detected compared to the baseline? So Entropic found most crashes faster than deep fuzzer, and they also found some new crashes. So in this graph, it just shows the X percentage of runs that crashed in Y number of hours or less. So the dashed line is for Entropic and the solid line is deep fuzzer. So maybe for example, we looked at 3%. So in 3% of the runs, Entropic finds the crash in less number of hours than deep fuzzer. So
entropy is the dashed one, right?
Yeah.
The dashed lines is find. Okay, so that means the deep fuzzer can still effectively find a lot of errors, but need more time.
Yeah. So how does the abundance threshold influence the performance? So basically, to repeat the idea, only incidence frequencies of rare species are used when computing a seed's energy. So this overcomes the challenge of overly abundant species dominating the energy values. And they found that entropy performs the best for an abundance threshold of 4096 or 1000 in hexadecimals. So, so this is the table that shows the original mean coverage for these subjects. And then based on different values for the abundance threshold, we can see what is the mean coverage for using that abundance threshold. So the one that I bolded shows that there is statistical significance based on the effect size. So you can see that for the abundance threshold of 1000, it shows that the mean coverage is usually more for this column. And another thing they notice is that the best performing threshold values appear to be subject specific. So, so for example, for this open SSL, you can see that actually the threshold value of 10,000 is actually better compared to 1,000. So this is another area of improvement. Maybe they can use some hyperparameter to tune the abundance threshold based on the subject.
Okay.
And lastly, what is the cost of maintaining the incidence frequencies? So these are the 12 example subjects, and the y-axis is just the proportion of the execution. So the frequency updates is basically the one that is added by Entropic, and then the dark gray one is the fuzzer maintenance, and the light gray one is the subject execution, where you're actually executing the program. So the black color boxes are basically the time. And
sorry, the subject execution, that means it will take an overhead to will have an overhead to slow down the subject execution, right?
Sorry, what do you mean?
I mean, here there's a in this diagram, you're talking about the proportion execution, and the proportion execution is this execution is just about an overhead or the overall fuzzing execution.
Yeah, it's the overall fuzzing execution.
So for now, that means so for some subject, it's okay. The cost of the different costs actually varies in different subject, right?
Yeah.
Okay, and actually there's 10 budget here. No, it's 12 budget. Why there's a 12 bucket?
Just 12 different subjects.
It's just pick up 12 subject. Why not 100? Why not 264?
I'm not very sure about that.
Maybe they sample the subject to find that the different subject, the overhead will varies in different subjects. Okay. But it seems that for some subject, like the last one, the overhead also almost takes the half of the overhead, right?
Yeah, but yeah, the dark gray one is the usual fuzzer maintenance algorithm. So the black box is the one that is added by Entropic.
Okay.
Yeah. So there's only like a 2% median overhead for maintaining the incidence frequencies.
Okay.
And if you just compare the time they spent in the fuzzer, then it's a 12% overhead. Yeah. but despite this overhead, Entropic still outperforms the baseline. So in conclusion, Entropy is the first grid-walk puzzle that leverages Shannon's entropy for scheduling seeds, and they prefer seeds that reveal more information about the software under test. And from the empirical study, you can see that this approach helps with boosting fuzzing performance in both code coverage and bug finding ability. Yeah, so that's it for this presentation.
Okay, thanks, Aaron. So I think the presentations are fairly clear. But I have the questions. And for Aaron, so you have, I think you have rich experience of using testing tool. So from your point of view, what do you think about this approach?
I mean,
do you think, and so maybe I can make it more specific. I maybe ask a two general question. Do you think, how do you think this approach, because this approach is designed for fuzzing, but the idea between fuzzing and testing are very similar. Do you think we can adopt, do you think this approach will be useful to improve our approach? Or do you think some kind of technique has already somehow adopted in an implicit way?
So, I mean, they're using entropy. In this case, they're using entropy as sort of like the fitness value in the terms of SBST. So basically, they are trying to use entropy to guide the schedule to pick the better seeds. And in SBST, this is done by using the fitness value or like the branch coverage to guide the search algorithm. So I'm also not very sure how this can how we can use entropy in terms of SBST.
Yeah, so I share the same opinions with you. For fuzzing, so I think one of the most important assumptions between one of the most important different assumptions that for SBSTs we have branch distance. We have already now given a test case and how far it is to cover this branch. But for fuzzings, they usually don't know. But they might know, but I don't know why they usually don't implement it. Maybe that's the difference between the Java bytecode and the x68 instruction set. So there's not such a, but I believe we can do this because for LLVM, do you know LLVM? So it is actually an intermediate representations of the source code. So these intermediate representations have lower levels than the source code, but have a higher level than x86 instructions. So for the x86 instruction, it will have some very detailed information like the memory address, the registers. But for LLVM, the form is very similar to the assembly code, but it will still hide some very detailed hardware information. So that's called intermediate representations. Java bytecode is a very special or very famous intermediate representations. As long as we have the intermediate representations, we can just manipulate it and instrument the details of branch distance. I think the fuzzing can work as well as I think the fuzzing can very improve it. And for this entropy, so my gut feeling is that the measurement of entropy, somehow trying to find the best scheduling or they're going to locate the low-hanging fruit as soon as possible. That's my gut feelings, because you can see once we explore something new, we give him more power to assign this seed with more energy, right? So this is somehow a little bit heuristics, but it does not care about the distance, does not care about past conditions. So my gut feeling is that as long as we give the further enough time, the branch covered by the entropic can always be covered by the label further. That is my gut feelings, of course. But when we read this paper, I think one of the things we can learn from it is that how to write a good paper. Basically, this approach adopts the very simple ideas, but it's presented in a very formalized and mathematical way. And the paper is well writings, and we can also see that the experiment is well designed and presented. I think that's a part we should learn. Yeah, we can talk more. We can discuss this. Discuss more this later. And also, I have passed you a few PhD advertisement. I think you have received it.
Yeah.
Yeah, you can consider it. Maybe we can talk more on tomorrow.
Okay.
Okay, thanks, Aaron. And the next one, Xianglin.
Yeah.
Yeah, Xianglin, really. I observed that you have very elegant slides prepared. Sharing the group.
Can you see my slides?
Yeah. Yes.
Which,
Yeah.
So the paper I'm going to present today is called Axiomatic Attribution for Deep Network, and it is published in ICML at
And this I like this title, axiomatic attribution.
Yeah.
So it can, but there's always there's also always problems. So if these attributions is axiomatic, that means every people can see it, right? For example, the gradient. I think the gradient is one of the most axiomatic or obvious attributions, but in this paper, they're actually saying it's not correct. It provide a more systematic, but it's called their systematic approach for the axiomatic. Very interesting. Please go on.
Yeah, so I didn't find the picture of the first author, but I think all of the authors are from Google,
Google research, yeah.
and they are all
Google gave
research
me a
scientists.
feeling that they either not publish. As long as they publish, they make a surprise. And then always, and these papers always have a lot of citations.
And the last author actually graduated from Shanghai
Shanghai University.
Yeah, and he pursued his PhD in Stanford University.
Okay, you can.
Yeah.
If you did it good, I think if you did good, you can consider an internship on 2 or 3 years later to join Microsoft or Google as an intern. Yeah. So it's well fun. You can consider them. You can consider the opportunity. Of course, you need to you need to good enough to be get admitted.
Oh, okay.
Okay.
So the background. So you can look at this picture. And the network might label the image as firebolt, but we don't know why. So that's the intuition for this paper. So basically, the goal of this paper is to understand the input-output behavior of the deep neural network. For example, in object recognition network prediction, we wanted to know the attribution of each pixels, and or in a diagnostic network prediction, we wanted to know which symptoms or measurement or history would let the model to predict the late I don't know how to.
So what's your point? So you want to see that which part of the images is explainable to the final decisions made by the model?
Yeah.
Yeah.
So first, let me formally define the attribution problem. So suppose we have a function f that maps a high dimensional vector to a value between 0 and 1. that represent a deep network. And we have an input that has n random variables from x1 to xn. And an attribution of the prediction at input x relative to a baseline input x prime is a vector from a1 to an. So for example, suppose the baseline is x1 prime, x2 prime to xn prime. Then a1 would equals to the attribution of x1 and x2 prime to xn prime. That means we only replace the xi to the input, and the other variables would remain the same with baseline. Yeah.
Okay.
So.
Well, sorry, let me read the last sentence. So there's the baseline x prime, and the attribution
So
x
for
and x
example,
prime, and the attribution x and x prime is a vector of a1 to an, where ai is the attribution.
You just replace.
So, yeah. So
we have a base.
May I ask? Maybe I missed it. So would you point out how to extract these knowledges? How to extract these knowledges from these definitions? So which part of the definitions indicate that this x need to be fixed?
So we just replace the xi to the input, and the other one would remain the same with the baseline.
Yeah, I get your point. So this is your red label.
But
I'm asking that how do you?
From,
this is your understanding. So I'm asking
reading the paper and
reading the whole paper or reading this definition.
With the paper.
With the whole papers, but that means we haven't got it. So it is not enough to extract this information from the definition. Yeah, the definition.
But anyway, that's my understanding of this.
I get it. I think this point is still somehow relevant to the ACE, right? The average causal effect. So yeah, it's an attribution. Yeah, so somehow maybe we can extract these meanings from this one. XI, AI, yeah. So that's the way. But anyway.
But this is my understanding, and I think other part of the paper instantiate my
support your understanding. Yeah. Okay, that's good. Okay, please go on.
But the challenge is when the researcher propose any attribution method, and the attribution method might report some misbehavior, but it's hard to tell whether this misbehavior stems from the attribution method itself or the model. So that's why they would propose some axioms, and they claim that as long as your attribution method can satisfy all the axioms, then the error can only come from the model, not from your attribution method. So yeah, the contribution of this paper is they propose some axioms that all the attribution methods should follow, and also they establish a new method called integrated gradient that satisfies all the axioms they propose. Finally, they do some empirical experiment over some deep neural networks to support their method.
Okay, that's great. Fairly clear here.
So before introducing integrate gradient, let me first introduce the generalized integrate gradient, which is called path method. So this is a collection. The path method is a collection of different integrated gradient. So the path method, let me see. Given a path function gamma, path integrated gradients are obtained by integrating the gradients along the path gamma alpha. So basically, for example, here we have baseline R1, R2. So R1, R2 is the coordinates. Maybe R1 is X coordinates and R2 is Y from Y coordinates. So basically, we link the baseline to our input S, and there might be a lot of past measurement available. So past method is more generalized, and the formal definition of past integrate gradients within each dimension I is defined as this formula. I think it's quite straightforward.
The gamma. Yeah.
So alpha is
so how what is F mean? F is the neural network model, right? The deep network.
Yes.
The smallest function. So
gamma alpha, because gamma is a path, so gamma alpha is just the dot over the points along that path.
I get a point. So but for here, giving the chain rule we can, whatever gamma is, the value is the same. Sorry, it's not. Am I correct? So this is an integrand for. So is this alpha is independent of gamma, right?
Yes.
And so that means whatever gamma function is, the value of this. I heard the voice of Yuan. Okay, so whatever it is. So whatever it is, so these values will always the same, whatever path it is. Am I correct? So suppose I have another gamma here, the value will be different. I mean the whole value, the integral value. Because again the chain rule, the f, the partial f over partial gamma, and multiply the partial gamma over partial alpha, so it can be replaced by the partial f over partial alpha. And here there's no gamma in this formula.
We have gamma, for example, for path P1, and each we are using the points along this along
with the path.
So basically, gamma alpha is, for example, here alpha equals to 0.5, right? This is gamma of 1, 0.5. This is the point, and for example, we have for path 2, this is gamma to 0.5. So when you use different paths, the gamma alpha is different.
The gamma alpha is different. But I'm asking that whether the value of this integral value, the value of this integral formula preserves the value, or whether the value the value of integral formulas is independent of the gamma function.
I think they are different.
So the answer is no. So when we choose different gamma, so when we do the integral through different paths, you mean the value
would be different.
Will be changed.
Later, when we talk about one axiom called symmetry preserve, we will talk about this. They actually compare different paths, different path method. Yeah.
Okay.
So in their method, it is called integrated gradient, and from all the paths available, they choose. They only consider the straight line between baseline and input. So actually, I prepared a question here, but But anyways, so the path is just P2, straight from the baseline.
So you give an answer now already.
Yeah,
Mm,
no many people here today. So
okay.
so I also give you the
You can ask a
proof.
phone maybe.
I have other questions later.
Okay, sure.
Yeah. So remember the path integrate gradient is defined as the formula here. So when we choose the straight line, which is P2, gamma I alpha is equal to this formula. So we can replace by calculate the derivative of gamma with respect to alpha. We can replace this part with this formula. So that's why we get the formula.
That's why we have here.
Yeah.
Okay, that's the definition why we derive here.
Yes.
Of course, I still have the confusions and with you. So we.
What confusion?
The confusion is that at the very beginning, I see these formulas. I somehow have the problem to understand what does this component means. And so I try to replace it with an T.
I come up with a new proof for the conservative completeness later.
Okay, that's great.
So, so basically, this slide tells you that we choose the straight line between baseline and input. Let me clear. Okay, so and then this paper proposed 4 axioms that all the attribution methods should satisfy. Actually, I would talk about 5 axioms, but one of the axioms actually comes from the average causal effect paper. But in this paper, they only propose 4 axioms. And to recap a little bit, the average causal effect is defined as the expectation when you intervent xi, for example, xi is your input and you intervent it to be alpha, and you go through your whole training data set and calculate the expectation of output y, and then you minus the expectation of y when xi is equals to baseline xi hat. So this is average causal effect. And first, the completeness, also known as conservativeness. Remember the definition of attribution we talked about before. So basically, the completeness means when you sum up all the attribution from A1 to AN, it should be equal to the output of F. The output of F at input minus at baseline. So it should be much more clear this time.
The definition is always clear.
Yeah, okay. So let's look at gradient method. So I use a very simple examples here. Suppose F on the output of F only determines by x1 x2, so F is equal to x1 times x2, and our baseline should be 0 0 and input should be 2 and 3. So like maybe Zhengfen can tell whether gradient can satisfy these axioms or not, and maybe you can use this simple example to support your idea.
The gradient is what gradient?
The gradient is the partial derivative, right?
Yeah. Let me write. So the gradient, for example, x1, x2. So this is attribution for 1.
For x1, yeah,
A1.
that's definitely.
A1. So if maybe you can use this. As long as it follows this formula, then the gradient method satisfies this axiom.
Zhengfen, would you please have a try?
Okay.
So I already
Mm.
calculated the A1
Yeah.
for you. I think.
Maybe you can first calculate the value of this one, so that will be much easier. And then you follow Xianglin's idea to calculate another two to see whether this formula holds true.
Okay, so value for input
IMP
is
is input.
Yeah, maybe you can write
Yeah,
something. Maybe you can think and you can
6,
write.
right?
Yeah. Yes. Yes.
and
This one.
0.
Yes.
right?
Yes.
Yeah, so the value should be 6, right?
Yeah.
Mm.
But
And yeah,
Then you calculate this one. You have
the
calculated these two. Then you calculated the sigma on attribute. Right.
sorry.
No,
so
you have calculated the right part, but you still need to calculate the left part.
and if
Okay.
they are equal, then yeah, the gradient method should satisfy this axiom.
How can I compute this one by the gradient?
So So ATR ATRI.
Sorry,
It's
I
okay.
cleared it.
So AT here we have two variables, so you only calculate ATR1 and ATR2.
ATR1 is 2, right?
ATR1 is
2.
It's gradient, so ATR1 is the derivative of f with respect to x1. So
Okay, so should be 3.
Yeah.
Okay.
And then ATR2
should be 2.
Yeah.
Right?
And then you sum them together.
But this one is 5. But
Yeah.
This one is 6.
So
Yeah.
So the conclusion is
No.
okay.
Yeah.
Yeah, you're correct. Yeah.
Okay. Okay.
Yeah. So let me clear the. Oh, okay. So and then for integrate gradient, and the answer is the integrate gradient satisfy this axiom. So let me explain my proof. So when each time we only look at one dimension. So suppose here we only look at dimension I. And remember, the path we choose is a straight line from baseline to the input. So here our path should be this one, right? And when you look at this formula, and I try to replace alpha with xi.
Okay.
So actually here alpha equals to 0 and here alpha equals to 1, right? Because this variable is right. You start from xi prime, and you add alpha times this line. So when alpha equals to 0, you begin from x prime, which is our baseline, and then when alpha equals to 1, you go to our input x. Right?
Yeah. So you're talking about this step.
Yeah. So when you replace when alpha equals to 0 and I replace it with xi prime, and we end up at xi. But the problem is
Alpha. How to replace
alpha? Yeah. So because alpha is start from 0 and end up at 1, and if we replace it with x, so I think we need to divide it by xi minus xi prime. So this length. Oh, sorry. So I think we need to divide it by the length of the path.
I once discussed with Ruofan on this formula as well. So Zhengfeng, did you understand this? I think this is correct, and we have a hello, Zhenfeng.
Yes.
You
I
understand
think
this?
it's
Mm.
right because alpha is
Yeah, the point is that F is I agree with you about the whole process, except notation. So how
so
to calculate fxi?
fxi.
Yeah,
So
fxi
I think
because f is a function. F is a function. So suppose x is a function to take a vector into input, right? Suppose here, and xi is actually one dimension of the vector. And what does this fxi mean?
I think
So what
here
I
we
do,
only
what
look
I do is, once I was with you, I do not dare to use this annotation. So what I use is that using a sigma xi prime to x and fx over xi. So that's all I do here. So all I do is I do not dare to write this one
okay.
into this one. Right.
But I think this only means we only look at the
One
ith
dimension.
dimension,
Yeah.
and finally we sum them together.
Yeah.
But anyway.
Okay.
Yeah.
Okay. So I think this is very like this almost the same as what I my Photoshop my photos in the group. Okay, that's great.
Okay. So let's move to the next slide.
Hello, Zhenfeng. You get the point?
I think I
Maybe partially. Maybe you can recap this and all the video is put on YouTube. If you have a problem,
okay.
you can ask Xianglin's advice. Okay,
Mm,
let's go on.
And average causal effect, it is not it do not satisfy this axiom because when you look at this axiom, you only look at one input and one baseline. But in our average causal effect, they need to go through the whole training data set. So the average causal effect do not satisfy for just one input. That's why they said average causal effect do not satisfy this axiom. But I think from the expectation point of view, the high level idea, the average causal effect did follow this this axiom, right? Because
yeah, I understand this.
the input, the expectation of input y minus the expectation. So here they just said it do not satisfy for just one input.
So this is what the paper said. In ACE paper.
Yeah.
ACE paper. Yeah. My would you please mention again? So my gut feeling is that they might be close. They might not exactly to conform to formula, but they somehow
the high level idea is
for example, suppose this value will be 6 and this value after the expectations might be 5.8, something like this. That's it, because we cannot 100%
yeah that's a
to get
that's
the
idea.
expectation. Okay.
And then sensitivity, actually they have two parts of sensitivity. Sensitivity A is for every input and baseline that differs in one features but have different predictions, then the differing features should be given a non-zero attribution. And the sensitivity just says if your variables do not would not affect your output, then the attributions should give this variable a zero attribution. And I think for this axiom, all the three methods satisfy the axiom, and it's quite obvious. So I don't think we need to explain this.
Do you think the gradient conform to the sensitivity?
Yeah.
Somehow it's not true, right? So sometimes the gradient is equal to 0, but it just do have an attribution.
Oh.
Right. So somehow,
Okay.
somehow like this. Suppose there's gradients and it becomes 0, right? This range, the gradient of this g here is 0. And when we calculate the gradient here, it give us 0.
Oh.
But when we calculate
Oh.
f0 and f(x)(y), this is x space, this is x. So there we have a difference about attribution.
Oh. Okay. So
So,
sorry.
yeah.
I forget when I'm making these slides. I forget about this. So gradient do not satisfy this.
I just have a gut feeling of that. so it seems that's not that straightforward.
Okay. Oh, so okay, sorry. But the integrate gradient and average causal effect all satisfy this axiom. And then let's look at implementation invariance. So here we have two definitions. The first definition is for functionality equivalent. So it says if two networks shares the same output for all inputs, then they are functionality equivalent. And the formal definition for implementation invariance is attribution method should satisfy implementation invariance as that is the attribution are always identical for two functionality equivalent network. That means yeah, for all input x, the attribution for x in the F1 network should be equals to the attribution for x in the F2 network. So that's implementation invariance. So this also tells you like the attribution should assign the credit or blame for the output to the input features and do not depend on implementation details.
Yeah.
And first here we need to clear one thing, that the gradients are invariant to implementation. So in fact, the chain rules support this idea. So we might have a lot of hidden layers. So here, suppose our input is a neuron F and output is a neuron G. And F should be the implementation details. And by chain rules, we only care about the derivative of F with respect to G, and we don't care about the implementation details. So gradients are invariant to the implementation. This is also the proof from their paper.
Okay.
So here I ask a simple question. So do gradients method and integrated gradients satisfy this axiom? Maybe Zhengfeng.
Hello, Zhengfeng. Is Zhengfeng there? The gradient integrated methods satisfy. So giving the assumption. So I'm still, of course, even I still think about here. So we have the chain rule. So by theory, the gradients are independent of how it's implemented. So whatever h and g it is, whatever h it is,
yeah,
as long as there's the gradients here, and
it should be invariant.
The partial derivative of f over g will always remain the same.
Yeah.
Okay, based on these knowledges, so do you think the gradients and the integrity gradients can satisfy this axiom of implementation invariance? So actually, this actually just the one choice, yes or no, right? Maybe whether gradients satisfy the axiom or the integrity gradients satisfy the axiom.
Hmm. The answer is just from, you can see it from the slides. Zhengfeng, did I lose connection on? Or?
I'm not quite sure actually.
So
Yes.
yeah. So you have a correct answer.
Oh, correct guess.
Oh.
Any explanation for that? Yeah, I'm thinking about here the gradients. Let me think about gradients.
As long as the gradients are invariant to implementation, then
yeah, I understand.
look at the formula. Yeah.
And also there's another knowledge for us. Another fact is that all the inputs will generate the same output.
Yeah.
Yeah. Okay.
So
I'm kind of convinced. Yeah.
Yeah. So for average causal effect, we only care about the input and output. So just by the definition, it satisfies this axiom.
Yeah, this is the definition.
This is quite clear. And then let's look at symmetry preserving. So the intuition for this axiom is when two input variables are symmetric with respect to a function, is if swapping them does not change the output value, then our attribution should assign the same value for those two variables. So here we have a simple example. For example, so if f is a sigmoid of x1 plus x2 plus some other values, so x1 and x2 are symmetric variables for this model. So for any attribution method, they should always assign the same the same attribution values for x1 and x2. So this is quite
straightforward.
very straightforward. Yeah, straightforward. And for the gradient method, yeah, I use the old example again. So maybe Zhengfeng, you can.
Maybe we can give chance to other
Okay.
people.
Okay.
And
Maybe ask another. Maybe Ruofan. Hello, Ruofan. Are you here?
Hello. Yeah, I think gradient method does not satisfy this axiom because the partial derivative with respect to x1 and x2 are different, but actually x1 and x2 are symmetric.
Yeah. Excellent.
Okay.
And for the integral gradient method, so first, actually, here they have a theorem that said integrate gradients is the only path method that is symmetry preserving. That means from all the paths that is available, they think their path, that the straight line is the only path that would satisfy this
The symmetry preserving.
Yeah. So the proof is here. So for an input, we might have a lot of dimensions, but here for simpler explanation, we can only consider 2 dimension I and j, randomly 2 dimensions, but the idea is the same for all the dimensions. So suppose, because so the straight line is our method. Suppose there's another path that is this path, and we can always find the interval that satisfies xi is larger than xj. So this part, right? And here the function f is defined as if the minimum of xi and xj is less than a. So that means xi and xj might appear on this interval from 0 to a. The function f would equals to 0, which is a constant. So in this case, the attribution for xi and xj
The
should
minimum
be,
xi and j is smaller than I. So
so
yeah, so that means that is a range, right?
oh yeah, the range.
It should be somehow
Oh yeah. So,
like this area.
but we only consider this path.
Okay.
This example, so it should be appear in this.
Okay.
Line. And if max xi and xj is larger than b, so they appear here. Right. The output is also a constant. So.
So this area, okay.
Yeah. So in those two areas, because the output is a constant, so the attribution should be 0. The attribution for variable should be
so
0.
what is the middle is the f is okay. The attribution when
because the output is a constant, then the attribution for the variable is 0. And then if xi and xj all falls in the range from a to b, then the function, the output f is xi minus a times xj minus a. So they are symmetric, right?
Yes.
So when t belongs to t1 to t2, that means the points falls in the interval from a to b. Then the attribution for xi is xj minus a, right? You can calculate.
That's the gradients, yeah.
Yeah, the gradient. But xi, remember the xi is always larger than xj. That is the definition.
Xi is always larger, yeah.
So they are not symmetric.
This gradient is not symmetric, but we're talking about integrity gradients.
Yeah, the formula contains. Let me think about xi. And we have a gradient here. But if the gradient is different, then the output should be different.
Minus xj.
So this is one example to say that the integral gradient on the other path is not symmetric preserving.
Let me digest a little bit here. So suppose in the red and the purple areas, the fx is a constant, and in between the alpha is a variable. It will change on giving the value of xi and xj. So here,
because only if xi and xj lies in a straight line.
So the point is that as long as
they are different.
I get the point.
If they are not straight, then this path method is not symmetry preserving. So this actually support that their integrate gradient is the only unique path method that is symmetry preserving.
So is that the evidence of that to you use, and do you remember on the very beginnings I'm saying that do you remember
Yeah. So that's why I said
gamma
they are not
and gamma over alpha. So I'm talking about so this is alpha, right?
Right.
So alpha is 0 over 1. So I'm asking whether the value of this integral is independent of gamma. And you say no.
So I think it's no, yeah, right.
I think it's still yes. I think it's still yes because the change is, but only if the gamma is a line. Make sure these kind of integrate gradients are conform to the symmetry preserving property.
Let me think.
You can think
Sorry,
about it,
wait.
right? The only problem is that when we have this formula.
Oh, you mean for some dimension they are not the same, but when you sum them all together,
Yeah, they're the same. You can think about it. You can think about it. So this is 2-dimension, right? Suppose you can imagine there's another dimension called z, right? And the formula of f is the form of this curve, the f curve, is always the same, right? So you just want to have integrate from 0 to z0, or z0 to zk.
Okay, I think.
Right? The value from z0 to zk is the same, but they have different 3-dimensional paths to go from z0 to zk.
Oh,
right?
Oh, I think I understand because. And okay, I get it.
Okay.
So yeah.
Okay.
But other past method is not symmetry preserving. So this is also a reason why they choose the straight line instead of other paths.
Yeah. Okay.
And for the average causal effect method, this axiom holds because they directly calculate the expectation of output.
Yeah. Because for the
so,
ACE, they do not care about the internal implementations. They only observe the external behavior. So that will be fairly clear.
And then the last axiom is called input invariance. So this is the axiom proposed by the average causal effect paper. That means if two functions f1 and f2, if for all the input x, f1x always equals to f2x plus c, then the attribution for input x in function f1 should be equals to the attribution for input x plus c in the f2 network.
I get the point.
So the gradient method satisfied this axiom. And remember, before we talked about gradient is invariant to implementation. And they also did the experiment.
The gradient descendant to this is a special form of the symmetry preserving. Suppose we let x plus c equals y. So all the that means giving to variables x, y, and all their behaviors are the same.
Yeah.
So it's a special kind of.
It's not similar. It's
that means x and x plus c. These two. Sorry, they're different.
Yeah.
No, for the
F1 and F2 are two network, but
so in this case, input invariance is not an axiom. It's a combination of two axioms. That's a lemma. Am I correct? So can I go to a few slides before to make? So surface. The first axiom is called the implementation invariant.
Oh, so
right?
yeah. So if you replace x plus c with y, right?
Yeah, and this is the first axiom, and the next one, the next slide. The next slide is about the symmetry preserving.
Symmetry preserving only care about one network, but
okay, the one network.
two different variable.
Yeah, so 2 dimension, right? The one that the 2 dimension. Okay. So it's more like Sunny will go back to the previous slide. Yeah. So here, so the difference might be a combination, an enhancement of the implementation environment, right? Suppose giving one network,
Yeah,
let it
you can think of it
and
this way.
giving one network F1 and F1 and
F2,
Fx
Y.
F1x and F1y and have the same behaviors, and suppose there's a baseline x prime, they should have the same attribution. X and y should have the same attribution. I think this is fairly clear. Is that correct? And then when we combine with implementing variance, that would be the shift, and that would be, and also maybe extend that. Suppose we can maybe we can interrupt.
But here the x is the same, but that just means
it just define it defines the change. It also defines the restrict. It defines the constraints. X y should be x y should be the constant shape, and what if it's not a constant shape? And suppose, for example, maybe we can change it. We can rotate, and after rotations, for example, given images, if we rotate the cat, and it's still the cat, and the output is still the same. So in this case, we do not need to use so strong construction of the constant shape. We can still use rotations, etc. So.
Oh, you mean by like times x times a?
Yeah, x times a matrix. This actually is a linear matrix. Just to change the just for example rotation or enlarge it a bit. For example, if we enlarge the cat is still the cat. Or we shrink the cat is still the cat. Right? So there's supposed more.
There are more possibilities. Maybe you can come up with one more axiom and then you can publish.
Yeah, so that's the idea we talked about. So this input invariant is a little bit restricted. I think they have more diversified restrictions.
But from the experiment I will talk about later, actually they show a lot of the attribution methods are quite sensitive to this constant shift. But for the gradient method, for example, the network, from network 1, the input is from range, is in range from 0 to 1, and in network 2 they minus the constant shift is -1, so the range is from -1 to 0. So the input, the two networks should perform the same, should be functionality similar, functional equivalent, and the gradient is equivalent for the two networks. So this experiment supports that gradient method satisfy this axiom.
Okay.
And the average causal effect method also satisfy this axiom. Also, just look at the definition of it. Yeah, it's the same.
And how about the integrity?
The integrity gradient, they do not have a mathematical proof, but they did the experiment, and the experiment here. Let me this one. So when they add a constant shift to the input 7, then in the second network, the integrate gradient is different from network 1.
But the gradient is still different.
The gradient?
Yeah, this is gradient, right?
It's gradient times input.
Okay.
So
this is great.
because the input is different now. So.
Mm. But it's a shape. But it's the shape. I'm saying that
Shape.
the net so shape is this 7 and this 7. And these 7s add some shape, maybe add some colors in the background, right? According
Oh,
to
yeah,
the
yeah,
input
yeah.
invariance, the gradient should be the same.
The gradient is the same, yeah. But
no, the gradient is not the same. The gradient looks different. These two are look different now. So
the gradient should be the same, but the input is different. So gradient
okay.
times input is different.
Okay. Sorry. No, please go on.
So then here comes the experiment part. So the first experiment is in an object recognition network. So I think this is an empirical study of their method. For a lot of image, they calculate the integrate gradient. And remember, from the background slides, we talk about why we don't know why the model predict this picture to be firebolt. But when you look at the integrate gradient, it looks quite similar to a firebolt. Not similar, but you can see why the model have a wrong prediction. Not wrong. It is a firebolt.
So yeah, the firebolt.
I don't know. I don't know.
The point is that so I'm not that familiar with the concept of firebolt. So here, I think this example means that when we apply integrity gradients instead of gradients on the images, we have a better explanation.
Yes. Yes. That's the result. And then the diabetic
regional passive
prediction. Yeah. So basically, they overlap the integrate gradient with the original image and show that actually the Laysian from an expert says those 4 parts might have some problem, and the integrate gradient did find those 4 points.
So here is still
they only
have you ever read the paper of the GradCam?
GradCam.
Yeah, GradCam. No, GradCam plus. I think Wang Chao was reported.
Yeah, I
think
remember
Wang Chao was reported this. So I'm not sure whether the GradCam can also have such a yeah. So yeah.
Maybe.
Yeah. So anyway, we are in the process of understanding more literature for causality and explanation for model decision.
Yeah. And the third experiment is on a question classification. So the goal of a question classification is to identify the type of the answer it is seeking. So here they highlight those words that have a higher integrate gradient value or higher attribute value. So for example, for the first question, the model predicted it to be numeric, and the word that is highly relative to this prediction is how many. So in this way, they show you can trust this model because the model did look into the right word in the question. And the fourth experiment is on neural machine translation. So basically, the input is in English and the output is in German. But I don't know German. But here the idea is when the meaning of an English word and a German word is similar, then their attribution value is high.
Sorry, let me calculate. So usually the neural machine translation will have an encode is a decoder encoder-decoder architecture. So the input is this is maybe English, and this is the German,
Oh,
and this is input and this is output, right?
yeah,
And
yeah,
actually, and like after this could be used transformer or using the area-10, whatever it is, all the sentence, for the whole sentence will be compressed into a vector. And based on this vector, there still be a transformer or area-10. But what I learned is area-10, so it will generate another number. So in this case, my question is how to apply those IG or integrity gradients here. It's going to learn the, is that means that it learn, so this might be giving this a German sentences, and this is Y and this is X. So somehow it's using the integrity gradient to generate a matrix like this and to bring that the correspondence relation. That makes sense.
Yeah, so for example, I think the English end is the same with this German word, so their attribute attribution value is very high. So that's the idea. And yeah, so it comes to a conclusion. They solve the problem of attributing a network's prediction to its base features, and they propose a new attribution method, integrate gradient, and it is simple to implement. Actually, when they implement integrate gradient, they use, for example, m points to approximate the integral. So it's quite fast.
Yeah, so technically, do you think which one is more efficient, the integrity gradients or the ACE? I remember there's still a speed up and the runtime efficiency or optimization for ACE.
I didn't check the time, but I think for if it's Rn, and then the integral gradient would be much faster because
I still have the gut feeling, even if the ACE have some optimization.
But yeah, because they need to go through
the whole data set.
Even if they have some optimization process, but it's still I don't know. And they have a quite detailed explanation on integral gradients in GitHub. If you are interested, maybe you can run their code from this link. And yeah, so that's the presentation today.
Okay, I think that was great. So I think in these literature reviews, we just build up the knowledges, and I think after the presentation, you are the one who will have the most impressions on those integrity gradients, and somehow
actually I found there are a lot of other attribution methods, and they look quite interesting. And I think if I have time, I would check each one of them.
Yeah, so I think one is enough, and as far as I remember, I think the TensorFlow framework has already an integrated version of IG.
Oh, really?
Yeah, so if we want to do this, we just need to invoke it. And yeah, in the future, I think there's much way for us to using this technique. And personally, I favor IG over. I favor
average cost.
ACG. So, and also I think for ICGs, the axiom proposed by ICG, I think it's kind of limited. It's kind of limited, and it can be enlarged, and but we really need to investigate and to see what application we care about, and we may try different variants of this the attribution technique.
Okay.
Okay, thanks. That's a great talk. It's very, very clear. And by the way, is Nima here? Nima? Oh, sorry, Nima is kind of lost. So anyway, are you here? So can you follow what we discussed? So, the neural network on attribution problems and the fuzzing, the cybersecurity. No, this fuzzing is not cybersecurity. It's a software security problem. So
The fuzzing, yes, but the neural network, it was very difficult.
Okay, so maybe
I will
maybe
watch the video.
you can watch the videos and maybe read the papers. So
Mm.
sometimes we need to some preliminary knowledge for us to digest. So that's why I will actually assign the paper presentations 2 or 3 weeks ago. But I think even the presenter prepared in 1 week before. But anyway, that's good. Okay, thanks a lot everyone to attend it. I now focus on Zhengfeng preparing the examinations. Also Aaron. And thanks a lot. Okay, let's meet next Saturday. Okay,
Bye.
bye.
See you.